Hello everyone, welcome to this session on CS22032 Deep Neural Networks. I am Ms. Lavanya J, Assistant Professor in the Computer Science Engineering Department at Sri Venkateshwara College of Engineering. I will be guiding you through today's lesson. So in this session we will study Unit 2 Artificial Neural Networks. So in this unit, we will learn about how neural networks are built and how they work. We will also cover important topics such as multi-layer perceptrons, activation functions, and learning algorithms. So let's get started. So in this unit, we will going to cover these topics related to artificial neural network. First, we will learn about the multi-layer perceptron, which is a type of neural network with multiple layers of neurons. Next, we will discuss about activation functions. So it is which decide how the output of a neuron is calculated and introduce non-linearity into the network. Then next one is back propagation algorithm, the key method that allows a neural network to learn by adjusting weights based on errors. After that, model selection. So it helps us to choose the best network architecture and parameters for a given problem. And then next one is regularization techniques. It includes a weight decay and a dropout, which helps to prevent overfitting and improve the network's generalization ability. So at the end, you will have a solid understanding of these key concepts and how they help neural networks learn and perform effectively. So the main objective of this unit is you will gain a solid understanding of artificial neural networks and their key components. So by the end of this unit, you will be able to understand the structure of artificial neural networks. And also you will know how neurons are organized into layers, including the input, hidden and output layers. And also how the information flows through the network. Next, you will able to explain the multi-layer perceptron or MLP architecture. This includes understanding how hidden layers enable the network to learn non-linear patterns, making it more powerful than single-layer networks. You will also learn to describe activation functions and their roles. Activation functions like sigmoid, tanh, ReLU, and softmax determines whether a neuron fires and introduces nonlinearity, which is essential for solving complex problems. Another important learning objective is to understand backpropagation mathematically. You will see how the network computes the error at the output, propagates it backward, and updates weights using gradient descent to minimize error. We will also cover the model selection techniques helping you choose the right number of layers, neurons and activation functions for optimal performance. Finally, you will understand regularization methods including weight decay and dropout, which prevent overfitting and improve the network's ability to generalize to new data. So, in this, you will be equipped to design, train, and optimize effective neural networks for a wide range of applications. Artificial neural network. So it is also called as a ANN. It is a computational model inspired by the human brain. Just like our brain, it has billions of neurons that process the information. So ANN is made up of interconnected units called neurons. These neurons work together to process data, recognize patterns, and make decisions. The structure of an ANN has three main parts. First, the input layer, which receives the data. Next, the hidden layer, one or more layers that process the data and extract important features. And finally, the output layer, which produces the final result or prediction. So one of the most important feature of ANN is that they can learn from data. They adjust the strength of connections called weights based on the experience. So this helps them recognize patterns even in complex or noisy data. Once trained, the ANN can make predictions on new unseen data. This makes them extremely useful in applications like image recognition, speech processing, medical diagnosis, and forecasting. So ANNs are a very powerful tool that mimic the brain's learning ability and form the foundation of modern artificial intelligence and machine learning. ANN can automatically learn from examples, which means that they do not need to be explicitly programmed for every task. So during training, the network adjusts the weight of connections based on the input data and the resulting output error. So this process allows the network to improve its performance over time, becoming more accurate with experience. So second one is recognizing patterns. So one of the strengths of ANN is their ability to identify complex patterns and relationships within data. This makes them highly useful in tasks such as image recognition, speech recognition, and handwriting detection. ANNs can even handle noisy, incomplete, or non-linear data effectively, which traditional models often struggle with. So finally, making it's once ANN has learned from data, it can predict outcomes for new unseen inputs. This capability is widely used in forecasting, classification, and decision-making systems. Examples include weather prediction, stock price estimation, and medical diagnosis, where the network uses learned patterns to provide reliable predictions. Artificial neuron is inspired by a biological neuron in human brain. So it receives signals, processes them, and produces an output. This processing involves taking multiple inputs, assigning importance through weights, summing them, and passing the result through an activation function. So let's look at the components of an artificial neuron. First one is inputs. So the inputs are from x1, x2 up to xn. Inputs are the signals the neuron receives either from external data or from the outputs of neurons in the previous layer. Each input carries information about the features of the data. Second one, weights. So weights, it can be written as W1, W2 up to Wn. Each input is multiplied by a weight. Weights represents the importance or influence of each input. During training, the network adjusts these weights to minimize error and improve learning. Third one is summation function. The neuron calculates the weighted sum of all inputs using the formula summation equal z equal to summation of 128 I equal to 1 to the power of n w of x w of I into x of I. This function combines the contribution of all inputs into a single value. Fourth one is bias. A bias is added to the weighted sum of inputs before passing it to the activation function. It allows the neuron to shift the activation function, enabling the network to better fit the data. In simple terms, the bias acts like a adjustable constant, giving the neuron more flexibility in learning patterns. Fifth one is activation function. The activation function takes the weighted sum plus bias and converts it into the neuron's output. This function introduces nonlinearity, which is crucial because most real-world problems are nonlinear. Common activation functions include sigmoid, tanh, relu, and softmax, each with each with specific use cases in hidden or output layers. Sixth one is output. Output of y. The final output of the neuron denoted as y equal to summation of 128 w of I into x of I plus b, which is what the neuron passes to the next layer or serves as the final output. if it is the output layer. This output represents the neuron's decision or response based on the input it received. So the bias shifts the function, the activation function adds non-linearity, and the output is the final result that flows through the network, enabling the ANN to learn and make predictions. An artificial neuron takes multiple inputs, multiplies each input by a corresponding weight, adds a bias, and passes the result through an activation function. So mathematically, it can be written as y equal to f of summation of I equal to 1 to n w of I x of I plus b. Here, x of I is the inputs, w of I is the weights, b is bias, and f is activation function. So Xi, which represents the input signals which can come from external data or previous layers of the network. Wi are the weights associated with each input that determine the importance of that input in producing the output. Bias, which helps to shift the activation function, allowing the neuron to model patterns more flexibly. So F is the activation function which introduces non-linearity into the network. So common examples include sigmoid, ReLU and tanh, which these are the outputs of the neuron which either goes to the network layer of the next layer of the network or serves as a final prediction if it is in the output layer. So this single equation which captures how an artificial neuron processes information, and it weights the input, shifts the sum with a bias, and applies a nonlinear activation and generates an output. By connecting many neurons like this in layers, neural networks can learn complex patterns, make predictions, and solve real-world problems. And here is the example for artificial neuron network architecture. So on the left side, we see a biological neuron. The neuron receives signals through dendrites. These signals are processed in the cell body, which contains the nucleus. The processed signal travels down the axon and is sent out as an output to the other neurons. On the right side, we see the equivalent in an artificial neuron model. The inputs x1, x2 up to xn represent the incoming signals similar to dendrites receiving information. Each input is multiplied by a weights w1, w2 up to wn representing the strength or importance of that input. A bias term BIS added similar to an adjustable threshold that shifts the neuron's response. These weighted inputs are summed up to produce a value Z representing the linear function part of the neuron. This Z is passed through an activation function F which determines the final output Y. This function introduces non-linearity, allowing the neuron to model complex relationships. So this diagram visually connects the biological neuron structure and function with its mathematical and computational counterpart in artificial neural network. Multi-layer perceptron. An MLP consists of multiple layers of neurons. An input layer, one or more hidden layer, and output layer. Input layer for simple perceptrons which has no input layers, the MLP can model complex nonlinear relationships in data to these hidden layers. Each neuron in one layer is fully connected to every neuron in the next layer, and the network uses activation function to introduce nonlinearity. This allows the MLP to learn from data by adjusting the weights during training, making it very powerful for tasks like classification, regression, and pattern recognition. The MLP learns by forward propagating inputs through the network and then adjusting weights using algorithms like backpropagation during training to minimize the error between predicted and actual outputs. A feed-forward network, neural network consists of three main types of layers. The input layer, which receives the raw data or features from the outside world. One or more hidden layers where the network processes information by transforming inputs through neurons, and these layers enable the network to learn complex nonlinear patterns. Then the output layer, which produces the final result such as classification or prediction. So in this network, each neuron is fully connected to every neuron in the next layer. This means the outputs from one layer becomes inputs for all neurons in the following layer. So data flows only forward from input to output without any loops or cycles. This forward flow is what gives the network its name as a feed forward. Uh, Feed forward network are widely used in many applications including image recognition, speech processing and data classification. So it gives the ability to model complex functions through layered processing. Here is the simple example of a multi-layer perceptron. Here the input values are x1, x2 and x3. The input layer which receives the input values x1, x2 and x3, and it receives the raw data. So it could be anything from pixel values or image or numerical features of the data set from the data set. Okay, so the values from the input layer or passes through the hidden layer. So in a hidden layer, the real processing will happens in this layer. The neurons in this layer performs the mathematical transformations on the input data to extract meaningful patterns and features. The more hidden layers, the deeper the network, allowing it to learn more complex presentation. So after that, we have the output layer here. This layer produces the final result, such as the output will be like a cat or a dog, or in classification problems. So here is the example for multi-layer perceptron. So here is the detailed description of multi-layer perceptron. First, the input layer. So it is the initial layer that receives raw data. It could be anything from pixel value in an image to the numerical features from the data set. It simply passes this information to the next layer. Next one is hidden layers. So these are the intermediate layers where the real processing happens. The neurons in these layers perform mathematical transformation on the input data to extract meaningful patterns and features. The more hidden layers, the deeper the network, allowing it to learn more complex representations. And then finally, we have the output layer. This layer produces the final result such as category label like cat or dog in classification problems, or a continuous values for regression tasks. So the output is what the network predicts based on the input data it received. So together these layers allow the MLP to take raw data, learn patterns and provide meaningful predictions. So what is the need for hidden layer in artificial neural network? Hidden layers are the intermediate layers between the input and output layer. Their role is to perform complex computations on the input data that simple linear models cannot handle. If a network has no hidden layers, it behaves like a linear model, meaning it can only solve very simple problems such as the logical and or OR functions. However, many real-world problems involve nonlinear relationships that linear models cannot capture. Hidden layers enable the network to learn these nonlinear relationships by transforming raw input data into meaningful features through multiple mathematical operations. This process is often called feature extraction. Furthermore, the use of activation functions like ReLU, sigmoid or tanh within hidden layers introduce nonlinearity into the network, which is critical for modeling complex data. For example, problems like XOR logic function cannot be solved by a network without hidden layers. But once at least one hidden layer is added, the network can learn and correctly model XOR. Adding multiple hidden layers increases the network's ability to learn more sophisticated features, and this is the foundation of deep learning. Working of multi-layer perceptron. And MLP, multi-layer perceptron, is a feed-forward neural network that consists of a input layer, one or more hidden layer, and an output layer. The working of an MLP involves two main phases. First one is forward propagation, and second one is back propagation. So first, forward propagation. The input data is fed into the input layer. Each neuron in the network computes a weighted sum of the input and adds a bias, which can be expressed mathematically as Z equal to summation of Wi xi plus b. Here Wi is weight and xi is the input. So this result Zi is then passed through an activation function such as ReLU, sigmoid or tanh, which introduces non-linearity into the network. The output of each neuron is passed layer by layer until the final output is produced at the output layer. Second one is error calculation. So once the output is produced, it is compared with the target value. The error or loss is calculated using a loss function such as mean squared error for regression task or Crossy entropy loss for classical task. This error quantifies how far the network's predictions are from the actual target values and serves as a guide for adjusting the network during training. So forward propagation allows the network to take predictions based on input data, and the calculated error will later be used in back propagation to update the weights and improve the network's performance. So next one is back propagation. So in back propagation, the error calculated at the output layer is propagated backward through the network, moving from the output layer to the hidden layer. The network computes the partial derivative of the error with respect to each weight. This tells us how much each weight contributed to the error, allowing the network to know which weights needs adjustments. Finally, the weight update. Once the gradients are computed, the weights and biases are updated using gradient descent or its variance. So the main goal is minimize the error by adjusting the weights in the direction that reduces the loss. This process is repeated for multiple iterations called epochs until the network converges, meaning the error is minimized and the network has learned the underlying patterns in the data. So backpropagation combined with weight updates enables the MLP to learn from data, improving its performance with each training iterations. Advantages of multi-layer perceptron. So MLP can learn complex and non-linear relationships that a single layer perceptrons cannot handle. This makes them highly effective for real-world problems where patterns are rarely linear. Next one is they support multiple hidden layers, which enables deep future learning. The network can automatically extract and transform features from raw input data, reducing the need for manual feature engineering. Third one is MLP or Versalite and work well for both classification and regression problems, making them suitable for a wide range of applications. And then when trained with sufficient data, MLPs can provide high accuracy in predictions. So the architecture is also flexible. The number of layers and neurons can be adjusted according to the complexity of the problem. MLP are fault tolerant, meaning that small changes or noise in the input do not drastically affect the output, making the network robust. So finally, MLPs are widely applicable in many areas including pattern recognition, image processing, speech recognition, and prediction tasks, which is why they perform the backbone of many modern AI systems. Limitations of multi-layer perceptron. So MLP often require a large amount of training data to perform well. Without enough data, the network may fail to learn the underlying patterns effectively. Training is time consuming because the network must compute weighted sums, apply activation functions, and perform multiple weight updates across several layers. So third one is multi-layer perceptrons have a high computational cost, especially for deep networks with many hidden layers and neurons. This can require significant memory and processing power. So fourth one is MLPs are often considered black box models, meaning it is difficult to interpret their internal workings and understand exactly how decisions are made. The next one is they are prone to overfitting if not properly regularized. Overfitting occurs when the network learns the training data too well, including noise, and fails to generate to new data. So sixth one is selecting the optimal number of layers, neurons, and learning rate is challenging and usually requires experimentation or hyperparameter tuning. So seventh one is MLP performance is sensitive to initial weights and parameters, which can affect convergence and learning quality. So finally, standard MLPs are not suitable for a sequential or a time dependent data without modifications, such as using recurrent architectures. So while MLPs are powerful, their data requirements, computational cost, and interpretability issues are important considered when choosing them for a problem.